Welcome to classes on D and F block elements, and it is class number 20. Today, due to advent of higher secondary second year, I am not going to details of this class, but I will give you the some key points upon which whole questions answer will be asked. So, first of all, on a brief analysis, I will just first give you the electronic configuration of D block element. These elements are also called transition elements as it is in between S and P. The position of D block is in between S and P, hence it is transition elements. And there are other reasons of transition elements because there are very often transition of electrons occurs in D and F block elements. Hence, these are called D and F block elements, and the automatic electronic configuration of D and S block element is n minus 1d 110 and ns 12. So in a very shortcut way I am telling you there are some series in D block element. One is 3d series, other is 4d series. I will tell in details in F block element, that's why I am not repeating this one. In 3d, 4d, 5d series, first series, second series, third series. And if it is 3d, means here 3d, and we will just write what is S. S is actually 4s. So if it is 3, that is less of this. So if it is 4, this is 3. If it is 5, this is 4. If it is 6, this is 5. Like this. You yourself can do this or write the configuration yourself. But most importantly, I will explain some of the very interesting facts upon which if you have a knowledge, you can explain each and everything very easily. The first one is enthalpy of atomization. Enthalpy of atomization, and symbolically you can write HA. Many of you may not have the proper concept on enthalpy of atomization, and it is the very important property. Just simply if you know details of enthalpy of atomization and lone pair of unpaired of electron, upon these two facts maximum of the property of DNF block can be explained. So this is very important, enthalpy of atomization. So what is enthalpy of atomization? So enthalpy of atomization is nothing but is the amount of energy released in the conversion of 1 mole of atom, that is in the crystal lattice, 1 mole of crystal lattice to its constituent atom in gaseous states under standard condition. Is called standard enthalpy of atomization, and it is denoted as HA. So to understand this, you should know metallic bond. It is not just like as methane. What actually in case of this type covalent bond, what we actually explain as atomization means if you break all these atom and make them in atomic form, 1 carbon and 4 hydrogen atomic form, that amount of energy is called energy of enthalpy of atomization. But here in this case it is not the same. That is in the metal, say I am just explaining minutely, you follow. Say it is cobalt, it has a lot of free electron. What is metal? What is metallic bond? Lots of cations or kernels are in the sea of electron, is called metal or metallic bond. So in the metal there are free electrons, all the free electrons are delocalizing, changing its locality from one place to another. This free electron does what? They attached with cobalt, 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 a lot of cobalt. So these are the free electrons. These are the free electrons involved in metal to metal bond, and this is cation. So what is metallic bond? It is the bond between metal cation to free electron. Is called metallic bond. So in the metallic bond we get a lot of free electron, and this free electron makes bond with the kernel, metal kernel, positive ion of the metal, and these are called metallic bond. And in this metallic bond we see in a crystal one cobalt is connected with a lot of cobalt through metallic bond, and if you now want to break this all bond, that needs amount of energy to make a constituent cobalt, single cobalt atom. That single cobalt atom, when it is in a singular form, is nothing but gaseous state. That becomes gaseous state. That is called enthalpy of atomization. Amount of energy required to break all this metallic bond, to convert each one into a single atom and single atom that is in gaseous form, is called enthalpy of atomization. Now enthalpy of atomization, say this is 1 mole, when it is converted into single atom cobalt in gaseous form, the energy required in the standard condition, it is called standard enthalpy of atomization. Now let me explain a bit more. Say in case of cobalt, or in metal, iron, cobalt, manganese, nickel, etc., you see there are two types of bond. One is metallic bond. Besides this, there are other covalent bond. So in covalent bond, what happens? This bond arises out of unpaired of electron due to one type of bond you have got, that is, if in the metal there is presence of some unpaired of electron, that unpaired electron will give rise to covalent type of bond besides metallic bond due to overlapping of dd orbital. And another is metal bonding, and another is covalent bonding. Metal bonding is due to metal and free electron. These are free electron. The free electron, delocalized free electron and metal bonds are called metal bond. And if there are some unpaired electron in it, that unpaired electrons are being utilized to form covalent bond. So two types of bonds we may get in metal in case of metal. So if there are unpairs of electrons already in the metal, so beside metallic bonds there are covalent bond. If there are no unpaired electrons, so there is only metallic bond. So now what are the factors upon which enthalpy of atomization depends? So factors are, number one, factors upon which enthalpy of atomization depends on unpaired number of electron. Number two, half filled, completely filled, orbital, and number three, is tremendously important, electrode potential. Later on I am coming to this one in my next class. So unpaired electron, this thing is very important. If there are more the number of unpaired electron, so besides metallic bond we need to break the covalent bond also. So there will be a lot of attractive force in the metal itself. besides metal-metal bonding, there are, due to the presence of unpaired electron, there are covalent also bonding due to overlapping of bonding. So number of bonding in the metal itself has increased. So amount of energy required to break all this bond to get constituent atom in gaseous form will also increase. So more the number of unpaired electron, more will be the atomization energy or enthalpy of atomization energy or standard enthalpy of atomization. Now second point is again important. Here, say in case of manganese, the electronic configuration of manganese is 3d5. So if you draw that block diagram of d5, 1 1 1, there are 5 unpaired electron. So it should have caused, due to the definition or the rule, more the number of unpaired electron, more is the bonding, more is the covalent bonding, more is the overlapping, more is the number of bonding besides metallic bonding. So huge amount of energy is to be required to make it a constituent atom or in gaseous form, means enthalpy of atomization should have increased. But mind that when this is in completely half-filled stage, it is stable. So it is not, this lone pair of electron is not willing to undergo bonding by disturbing its stability. Hence, there are presence of unpaired electron, yet it will not undergo any bonding. So it will not show any extra covalent bond, that is, it will not be effective. That is, unpaired electron, if it is in stable form, it will not undergo bonding and enthalpy of atomization will not increase. That's why unpaired electron in the metal orbit is a factor to decide whether enthalpy of atomization will increase or not. Now, if in zinc you will get 10. Again, if you draw the block diagram 10, if you draw the 5 part like this, 2 2 2 2 2 2, it is completely filled. Again you are getting that there are no unpaired electron. There are electrons in the d orbital, but all the electrons are paired up. It has got stability. It will not give rise to any type of extra bonding like covalent bonding. So enthalpy of atomization will decrease. So unpaired electron and half filled, completely filled, and enthalpy, that is electrode potential, standard electrode potential, it is a factor I will explain in details in my next class. If the enthalpy E naught is more, the HA is directly proportional, will be more. I will explain it later on. So for time being, if you keep it in your mind, you can able to understand or answer a lots of question. I will at this instant of time will solve out. Manganese, it is in 3D, and technetium, it is in 4D. Now from scandium, titanium, vanadium, chromium, manganese, iron, copper up to zinc, it is 3D. So in 3D series we get manganese, atomic number is 25, and we get its configuration as 3. If I ask you what will be its enthalpy of atomization with respect of others, it will have enthalpy of atomization less, because all the unpaired electrons have given rise to stable half-filled orbital condition, half-filled population of electron, and it is very stable, and this half-filled, completely half-filled arrangement will never undergo bonding, and bonding will not increase. So enthalpy of atomization will not increase. It will have less enthalpy of atomization in 3D series. In technetium also, due to same fact, it will have in 4D series, it will have less enthalpy of atomization. Next one is manganese and chromium. It is atomic number is 24 and its atomic number is 25. In the exam it is asked enthalpy of atomization of chromium is more than enthalpy of atomization of manganese. Again you will explain the unpaired electron of in chromium, you draw the configuration 3s2 3d4 or 3s1 3d5. So in both the cases you will find unpaired Yes, unpaired electron in chromium is more than this due to the presence of unpaired electron. uh, Besides metallic bonding, it has got some extra bonding, and due to this extra bonding, these extra bonding bonds are required to be broken to make an individual chromium. So chromium has got more enthalpy of atomization than manganese. Question number 2. Question number 3. Zinc, cadmium, mercury. Zinc, cadmium, mercury. Zinc in 3D, cadmium is 4D, and mercury in 5D. All have got configuration 10. We will come later on. These zinc doesn't show transition element characteristics, though it is placed in transition groups. Later on we will explain. So zinc, cadmium, mercury has not heard as other element in its series. Zinc is not heard as other group in the 3rd series. Cadmium is not heard as other element of 4D series, and mercury is not as hard as other element of 5D series. Answer: why? Because of completely filled electrons in 3D orbital, all zinc and cadmium doesn't have extra bonding, hence extra energy is not required to make the individual or constituent zinc atom in gaseous state, cadmium in gaseous state, mercury in gaseous state. Due to this fact, zinc, cadmium, mercury are not heard. They are not heard as others one, because their bonding is less and restricted to metallic bonding only. Next question's answer is iron has got more enthalpy of atomization than copper. If you write the configuration of iron, you will get D6. Am I right? Whenever D6, 1, 2, 3, 4, 5 and 6 pairing start, there is 4 unpaired electron. But if you draw the configuration, this one 4s1 3d 10, am I right? You will get the configuration here. The unpaired electron is more. Unpaired electron is more, 4 number, and here you will get unpaired electron is tremendously less in comparison to this one. Due to the presence of unpaired electron in it, besides metal bonding, there are other types of bonding. So metallic bonding interaction in it is more, so larger amount of energy is required to the all types of bonding present in this due to presence of unpaired of electron. Hence iron has got more enthalpy of atomization than copper. Next one is, again question appears, zinc has less enthalpy of atomization. Again the reason is the same as zinc is not hard, means no extra bonding is there in zinc besides metal bonding. Here due to this fact, no extra bonding is there in zinc besides metal bonding. So zinc doesn't have much enthalpy of atomization in comparison to other element in the 3D series. Next one is, you should first know what is the use of enthalpy of atomization so that you can understand its application. Enthalpy of atomization, actually it is directly related to uh, electrode potential, standard electrode potential, and hydration enthalpy. And electrode potential is uh, directly related to the oxidation and reduction property of the cation, and also stability of cation in solution, and very important is melting point and boiling point. Mind that melting point and boiling point is directly related to enthalpy of atomization. As more the enthalpy of atomization, more will be the melting and boiling point, more tightly the bonds are there, so more amount of energy will be supplied to melt or boil it. So more the enthalpy of atomization, more will be the melting and boiling point. But when we will go, if you compare the melting and boiling point property, you will find that from scandium to zinc, the property of melting and boiling point increases, and at certain time after chromium it is top. Am I right? Top. After this, scandium, titanium, vanadium, chromium, then manganese. Again, if you go on this up to this increase, because lone pair increases, more the lone pair, more will be the bonding, intermolecular attraction force is there, and besides metal bonding, due to the presence of unpaired electron, as it increases, as we move from scandium to chromium, it increases, its enthalpy of Ha will increase. But as we increase further, we get there is 5 electron, the 5 electron have got stable configuration, and this stable unpaired 5 electrons will no longer be used in formation of bonding, and hence enthalpy should not increase as it ought to be. Am I right? So manganese, scandium, titanium, chromium, manganese, iron, copper. Now again, if you when you approach this, you will find 5 electron, again 6 electron. If there is 5 electron, 1 2 5 electron, same manganese, 6 electron for next one, 7th electron for next, 8 electron, like this. So when you increase after 6, 5, 6 number of paired electron, if it is 6 paired electron, earlier 5, then unpaired electron will be 4, pairing will start. If it is 7, the again pairing starts, unpaired will decrease, again increase, pairing start, unpaired decreases. So when you move from left to right, at certain point the unpaired electron increases, and then when the unpaired electron goes in increasing, then pairing starts, and due to the pairing of this unpaired electron decreases, so melting point again start decreases, and this becomes 0, less. So this is the peak point. Am I right? So with the help of this, we can explain oxidation, we can explain reduction, oxidizing agents, reducing agent, oxidized, reduced, and then stability of cation in solution. Lot of questions are being asked in higher secondary final years, also in the entrance exam later on when coming, when we will explain this in an elaborate form. So with the help of this, we can find out this. Then hydration enthalpy. Hydrogen released, hydration enthalpy, amount of energy released when 1 mole of substance get hydrated in the solvent like water. It is very important things. The utility of this one I am explaining. So upon this one we will explain hydration enthalpy. And what does hydration enthalpy actually means? That is, it is nothing but bonding of the substance with water. Bonding with water is called hydration. So sometimes we see some cations or metal ions get bonded very easily with water and some doesn't. Am I right? So if the amount of energy released during this type of bonding with water, this amount of energy released during the hydration in solvent is called hydration energy. Now what does hydration? It is very important. It is very important. So first of all, I am telling what does hydration means. It is this. And how does hydration energy may be applied? If the more is the hydration energy of the metal ion in the solution, more will be its stability in the solution. Now how will be its mode? If the smaller size of the cation is the smaller, more will be the hydration energy. Why? Because if the size of the cation is small, then or charge of the cation is more, then more and more water molecule will get attached with this one. Polarizability effect will be more and water will be attached to one. So more will be its hydration energy. Now how this hydration energy helpful? We will take an example. Say one is copper, very often asked in the question, and copper 2 positive. If I ask you copper 1 positive and copper 2 positive, which one is more soluble, more stable in the solvent, in water? Answer, this one. Why not this one? First explanation, in the textbook, the answer is given one disproportionate reaction occurs. It is not exactly you have given this one, but you can't understand exactly what the meaning is. So copper and this, out of this, the size, in terms of size, it has got lesser size than this one. And also in charge of charge, more the charges, more is the polarizability, less is Fajans rule. Less is the smaller size, more is the polarizability, more is the attachment of water molecule with it, and more is the plus charge, more is also polarizability, more will be stability, hydration chances, and more will be the hydration energy. So due to as the hydration enthalpy in its is more, and more water molecule will be hydrated here in case instead of this one, due to smaller in size and greater in charges. So copper 2 positive is soluble in water, not copper 1 positive. But simply in the book you will find that another reason is given, that is also true, that copper transform to copper. This type of reaction is called disproportionation reaction. Disproportionation reaction, the reaction in which a single cation, once it is oxidized, other it is reduced. Single one, copper in mono plus, it has become 2 plus, means it has lost one oxygen, so it is oxidation from this to this. And from this copper, its one oxidation state is 0, the oxidation is state is become less, so it is reduction. So in single reaction, once you are getting loss of electron, sorry, next one it has gained one electron, am I right? Reduction, loss of electron, Leo is called oxidation, loss of electron. So this is oxidation means loss of electron is called oxidation. And here gain of gain of electron is called reduction. In one case it has lost electron, in other case it has gained one electron. So oxidation reduction process from the same cation species has occurred, since it is called disproportionate reaction. So in the explanation it is told that when copper 1 positive in solution, it undergoes disproportionation reaction, and that's why it is not stable. Now what does it actually mean? What happens if it is undergo disproportionate reaction? Then what happen? Why it will not be stable? It is not given. So you should understand what's happened actually here is, that is when it is in the solution, disproportionate reaction occurs. Means here from this and these 2 points, this is highly hydrated, hydrolyzed. So a bit earlier I have told you amount of energy released when 1 mole of substance is called hydrated in the solution is called hydration energy. So since it is linked with more and more water molecule, then this one it is hydrated in a greater extent, so more and more energy will be in the solution. So the excess amount of energy is here easily required to convert copper monopositive to copper 2 positive. Due to hydration, high extent of hydration, the energy released in the solution is helpful in converting copper 1 in the solution to instantly convert into copper 2 positive. Otherwise in normal form you can't, it will be huge amount of energy is required to copper 1 plus to copper 2 positive. Due to its hydration energy, that amount of energy, a part of energy is excess energy is used to convert to copper 2 positive. So if copper 1 positive is in the solution, instantly due to high hydration energy, it's convert to this one. This is the reason that undergo disproportionate reaction. But another fact is that if I have not come to this one, it is from thermodynamic point of view. This chapter has not been yet discussed by me. So if you calculate, you will find its value is 37.37 volt. So standard enthalpy is electrode potential is E naught is plus 37. So we know what is del G. Del G is equal to minus N if E naught. So now if you put this plus value here, again you are getting the answer as negative. So when del G is negative, the feasibility is a question mark. What will be the feasibility of the reaction if del G is negative? It will be spontaneous reaction. It will follow from left to right. The reaction will be forward. So in the reaction mixture, if there is any cationship plus positive, due to this factor in mind, if you put this one, you will find the reaction will instantly proceed towards right. That means copper 1 positive is very easily forward towards copper 2 positive if disproportional reaction occurs. That's why it is told that due to disproportional reactions of copper, the copper 2 positive is more stable than copper 1 positive in solution. Stop. So from this, just you can correlate something, though I have not exactly explained E naught, electrode potential. Now I have seen if E naught for copper in the solution is positive, then it is unstable. So the stability of ions in the solution can also be explained with the help of E naught, electrode potential. So more is the negative form of E naught, more is the E naught, more negative, more will be its stability in the solution. So if it is in positive, more and more positive, more is the solubility. Negative, more is the stability in the solution. That's why there is a question why copper. Later on we will explain when we will come with E naught concept. Okay. So metal bonding in 4D and 5D series is more than 3D series. Answer very simple. Again there is a concept. I am not elaborating the question's answer. Very simple, it is not tough, because metal bonding in 4D and 5D are more, or tendency of metal bonding in 4D and 5D is more than the 3D, because in 4D and 5D there is 4n and 5f orbital, and 4n and 5f has less shielding effect, that screening effect, and hence the free electrons are readily available for bonding with other metal. That's why they are very interested in bonding with the another metal. And another fact is that because of the greater size of 4 and 5D, bigger size of 4 and 5D series elements with respect to 3D series, the last free electrons are loosely bounded with the nucleus, and hence these are electrons are freely available for bonding with the metal. Hence metal bonding tendency is more in 4D and 5D. This is not much tough, very simple things, and question very often asked in the exam. Then question comes from this one: variable oxidation state. Transition elements show variable oxidation state. Very simple, because the energy difference between N1D, N-1D and NS is very less. Hence, both NS and N1D can participate in bonding. Since both the orbital can participate in bonding, they show variable oxidation state. Very simple. NS, N-1D both can participate in bonding, and they show variable oxidation state. Next one, again very simple. Paramagnetic character. Paramagnetic behavior or character. So I am not explaining, it is very simple again. Paramagnetic behaviors are very often seen in case of transition element, because of the presence of unpaired electron in d orbital. So due to the presence of unpaired electron in d orbital in transition elements or d block elements or block elements, they are very easily paramagnetic, attracted by the magnets, and the strength of magnetic attraction is given by the formula these two Bm. So mu is equal to n into n plus 2 Bm, where n is equal to number of unpaired electron. Number of unpaired electron, the formula is given. So more is the number of unpaired electron, more highly will be attracted by the magnet. So if you are asked arrange in increasing order of the magnetic attraction between some cations, you draw the configuration and find the unpaired electron and put the value in. If it is 1, the answer will be 1 point something. If it is 2, answer will be 2.8. If it is unpaired electron is 3, this will be 3.7. If it is 4, this will be 4.8. If it is 5, this is 5.9. What is the number of unpaired electron? Just you put in whole number. If it is 1, 1.7. It is 2, 2.8. If it is 3, 3.7. It will be 4, 4.8. It will be 5, 5.9. It will be 1, 2, 3, 4, 5, 6. Like this, you will find the value of mu. More the value of mu, more will be attracted. So more is the unpaired electron, more strongly it will be attracted by the magnet. Hence, they are called paramagnetic. They often show paramagnetic behavior. But if you think of zinc or other this one where there is no unpaired electron, again you draw the configuration and find whether there is unpaired electron in zinc, cadmium, or mercury. You will find there is not unpaired electron in zinc and cadmium, mercury. So you will find n is equal to 0. So it will not be attracted by the magnet. These are not paramagnetic behavior, but there are some unusual behaviors. So that's why zinc and cadmium, mercury, though they are placed in transition elements series or d blocks, they yet doesn't show many of the d character. They are not tough, they are not hard, they do not show color, they are not attracted by the magnets, and lots of things will come in bit by bit. So this is regarding paramagnetic behavior. Now another important, from each and every point I am discussing, the question very often comes: catalytic behavior. Catalytic behavior. So catalytic behavior, so you need not to explain much. You see, catalytic behavior is shown by the transition element because of their some vacancy in the d orbital first, and the d orbital elements have the tendency to exhibit variable oxidation states. And again there are some defects in the crystal of the metals. Due to the crystal defect in the metals, they show catalytic behavior. Very simple, again nothing to explain it in elaborate. You just simply explain vacant d orbital, tendency to exhibit variable oxidation state, defect in crystal. These are the reason for which they show catalytic behavior. Next one is color. Color is again due to, at the very beginning I told you, if you know HAN unpaired electron, each and everything can be explained. I am just showing you what's happened if there is unpair of electron in the d orbital. If there is unpair of electron d orbital, all the d orbital block 1, block 2, block 3, block 5 are degenerate states. More or less they have the same energy calculation in each and every block. If there are some vacancy or unpaired electrons are there, so one electron may jumps to other, again they come back, again another electron may jumps to another space, again they come back. So on jumping and coming back in both theory in the first year you have got, so when electron gets some amount of energy, when the electron absorb amount of energy, that absorbed energy with more energy, it jumps from one level to another level, again from that level it again come back to its initial back level after releasing that amount of energy, and that change of energy is equal to h nu is equal to hc by lambda. That energy difference gives rise to lambda, and lambda gives rise to color. So when there are vacancy, when there are unpaired of electrons, all the electrons are not paired up, there are some blocks are remain vacant, or there are some blocks, there are some electrons, there are unpaired electrons, there are chances of jumping of one electron to another one level to another d level. So d transition occurs, and due to this d transition on absorption of lights, that jumps from one to another and again come back. During when it comes back, that gives change in energy, and that change in energy according to d Bohr's theory, h nu is equal to hc by lambda, and lambda is related to the wavelengths related to the light. So they show light. So color is shown due to the presence of unpaired electron in d orbital, and there occurs jumping of electron from one d level to another d level, and this is called d transition. On absorbing light from the sun, it absorbs some amount of energy, and d transition occurs, and in this process we get h nu is equal to hc by lambda. C by lambda is related to the wavelength, hence it shows color. Find you can explain, you can understand that, give you the questions answer very easily. Complex formation, they have a very high tendency to form you don't write the lengthy questions answer is why complex formation occurs in d block element or transition element show a very keen tendency towards complex formation. This is only because of the fact that smaller size of the cations are small, smaller the size, smaller the ligand, and lots of things are there. If the size of the cations are small, they have the high tendency to form complex, and higher nuclear charge, again they are in comparison to their charge, the nuclear charge increasing or size decreasing, and due to the higher nuclear charges they have the ample chances, because they will get lone pair of electrons and lots of things, unpaired electrons. Am I right? And also there is a some when there is unpaired electron, there is a chance of d-d-d orbitals, and due to the all these facts, smaller in size, higher nuclear charges and overlapping in d-d-d orbital, chances of overlapping d-d orbitals in presence of the unpaired electrons, all these factors give rise to the tendency of the transition element to form complexes. Mind that osmium and ruthenium that has highest oxidation state 8, and has +2 to +7 highest oxidation number in the series, and highest oxidation state is this, and manganese has highest number of oxidation states +2, +3, +4, +5, +6, plus like this. Sorry, we see titanium and which one is colored and which one is not. Scandium and titanium. Scandium is 1, 11, 21. Configuration is atomic number is 21 and 23. So argon is 18. If you draw the configuration, you will find argon 18, am I right? And 18, 20, 23. So when you talk about scandium 3, there is a loss of 3 electrons. So if we lost 3 electrons, we get here 2 electron, and 1 electron we get 3d0. So since there is no d electron, so there is no chances of transition of electron dd transition, hence it will not show any color. Here in case of titanium 4, we need to remove 4 electron, 2 electron from here, 2 electron from here. We see there is 1 electron left, so it is cut. So simple, you draw the configuration. If you find there are d electrons are there, these are colored, and if you see d electrons are not there, this is colorless. Next one, another question: copper 2 positive in solution is colored, but zinc 2 positive in solution is colorless. Again, whenever you draw the configuration, you will see when copper 2 positive is, it is 29 electron configuration, you will find there is no electrons left in the d orbital, but in zinc positive 2 positive you will find d10 and s2 is 0. Am I right? Here you will get d is completely filled, and hence it is zinc is completely filled. Sorry, this is 29. Am I right? So from 29 the configuration is 4, 2 and 3d 29, and if you now remove this one, you write 1 and here we write 10. If you remove 2 electrons, you will get there are d electrons. Am I right? So it shows color due to the presence of electron, but here in case of this one, you will get 3d 3s2 3s2 4s2 and 3d10. If you remove these 2 electron to make it zinc 2 plus, you will get 3d is 10. It is completely filled. So if there is completely filled, there is no chances of transition of element. Hence zinc will not show color in solution, but copper will show. Cadmium, mercury, scandium, this is 3d10, 4d10, 5d10, d0, d0, all are colorless. Sometimes you are asked which one give color, which doesn't. Just you draw the configuration, you will find. The next and property is talk about the interstitial compound. Interstitial compound means in the transition elements in the crystal there is always void, there is gap, there is vacant space in the transition elements, and in this vacant space the small sized nonmetals hydrogen, boron, carbon, nitrogen can very easily tapped inside it, and this is called interstitial compound. Due to the presence of vacancy in the d orbital, they can very easily form interstitial compound. Now these interstitial compounds are chemical behavior have the same from in any interstitial metallic crystal. If you just enter some non-metals, so you are getting a new compound. The new compound will have the same chemical behavior before entrapping another non-metals. So their chemical behavior remains same, but what's happened, their physical behavior changes regarding the melting point or hardness, this and that, it will be affected. So their physical behavior changes in interstitial compound, but the chemical behavior remain the same. KMnO4 and K2Cr2O7. So the preparation, I am not going to the preparation and this and that. I will go to the questions which are very often asked in entrance exam in NEET 2023. There was a questions. There was a question ion exchange method to solve out, and that question was from this. I will just explain. I am skipping one part, that is stability of the ion in the solution. I will solve this part in the next class when I will explain E0, electrode potential. I will explain it in details. A lot of things is to be explained on this one to explain this stability of ions. Sometimes E0 is very applicable. So I have told E0 is plus, it is not soluble, it is not stable. E0 is minus, it is stable. So when there is a couple, what will happen? A lot of things are to be considered. So I will take it later on. So loss of electron is oxidation, gain of electron is called reduction. In speedy form I am showing you because you have got these things in higher secondary first year. So I will explain in short, in a quickest form, how to solve this one. So many of you know it is redox type of reactions where oxidation is one part, one half reaction, and reduction is one half. I will not work out all the steps how to solve. I will show you the trick how to solve within a short time. So first of all, you see from this one to this one, the oxidation stage has gone from 2 to 3. So the difference is 3 minus 2 is equal to 1. So nothing to do. If difference is 1, nothing to do. You give up this one. Come to this one. Here the oxidation state of manganese is 7. Am I right? Here oxidation state of manganese is 2. Minutely follow. Minutely follow, you can understand very easily. So what's happened? What is the difference? The difference of these two is 5. That difference you please place here 5 and that 5 here. Am I right? Difference of oxidation state of these two will be placed on the other one. So there are two reactions. two sets of reaction. One is oxidizing, other is reducing. One is giving electron, giving out electron, other is taking up electrons. Am I right? So from this to this, you can find out the oxidation state. You take it as x, and this is 2, 4 to the minus 8. X minus 8 is equal to minus 1. You will find 7. It is known. It is very simple. I am not explaining. Oxidation state of manganese is 7 to the 5. You would make difference. You will get 5. That 5 you place here 5, 1 5 here. Now come to this one. Come to oxygen. To tell if there is any oxygen further besides this oxygen. So add up all this. Now there is only one oxygen. Here one oxygen. This oxygen is equal to 4 in number. So if this is 4, so that should be 4. Put here 4. So to make this 4 oxygen equal, we are getting 4 to the 8 hydrogen. So here it is 8. This is nothing very simple. 1. I am just solving out one after another. You follow. Next one. So you see here manganese is equal to 7 and here manganese is equal to 2. So difference is 7 minus 2 is equal to 5. You give 5 here and 5 here. Now come to this one. Here oxidation is 2 and from S2 negative you have got S elementary form, that is 0. So 2 minus 0 is equal to 2. So that 2 go over this place. Am I right? So now you think of oxygen. Here oxygen, how many oxygens are there? 2, 4, 8. And here there is one oxygen, so 8 oxygen. When 8 oxygen balance, there is 16 hydrogen. We give here 16. Okay. So come to the next one. Yes, for this reaction to be balanced, we are getting two set of reactions as this. So in the first set, we have already calculated the oxidation state of chromium, that is 6, and this is 3. So difference of this oxidation states is 6 minus 3 is equal to 3. For 2 chromium is difference multiplied by 2 means 6, and that difference should be put in other set of half oxidation reaction, half redox reaction. And next one, chromium here 2 and here chromium 1, so make it 2. So these two half of reactions are already been balanced. Now come to number of oxygen. Here oxygen is equal to 7, so make it 7, we make it 7. So when oxygen is equal to 7, the hydrogen is 14. The second one is here in this reaction, you see the two reactions are like this. So from first one you balance it, 2 chromium, so 2 chromium. The first set is over. Now see here there is 7 hydrogen. So difference of these two oxidation state is, this is 6 and this is 3. So difference is 6 minus 3 is equal to 3. So for 2 carbon, 3 to the 6. So to make it 6, here you should be alert, because that it will not be 6. The multiplication of these two will be 6. So you put here 3. So if it is 3, this is 3. So two half cell reactions, redox reactions are being balanced. Now oxygen is 7. We have to make it 7. We need 7 for the 40. Again, for this reaction, two sets of reactions are like this. So here you are getting chromium 2. So to balance it, 2, oxidation state is 6 and here 3. 6 minus 3 is equal to 3. For 2 chromium it is 6. So you give here 6 and don't give it here 6 because 3 to the 6. 3 to the 6. Now come over to oxygen. Oxygen is equal to 7. So make it 7. We are getting hydrogen 14. So now here in this reaction, again two sets of reactions are like this. Here oxidation state is of manganese is equal to 7 and this is 2. 7 minus 2 is equal to 5. Give it 5 and this is 5. Here nitrogen, the oxidation state of nitrogen is 3 and it is 5. So difference is 5 minus 3 is equal to 2. So that difference should be here. This is 2. This is 2. Now come over to oxygen and you see how many oxygens are there. 4 to the 8 oxygen and 5 to the 10. 8 and 10, 18. Here 5 3 the 8, 15. So to make it 18 we need 3. To make oxygen 18 we need 3. So here 3. When 3, hydrogen is 6. Make it 6. Next. Now come to, let us solve this one. Here two sets of oxidation half and reduction half reactions are like this. So to make it balance, chromium 2 you make it 2. Am I right? So the oxidation state is equal to 6 and this is 3. 6 minus 3 is equal to 3. So for 1 chromium it is 3. So for 2 chromium it is 6. To give 6 here, 6 here. Am I right? So now come over to oxygen. Here oxygen is equal to 7. To make this oxygen 7, you give here 7. This will be 40. Now let us solve this one. The two half reactions are like this. Here oxidation is 7. Here oxidation is 4. The difference is 3. Am I right? So if the difference is 3, we should give here 3 and we should also give here 3. But it is double bimolecular, but it is monoatomic. Diatomic and monoatomic. So 3 to the 6. It is double 3. It is single. It will be 6. Am I right? So now come over to this one. The oxidation state of sulfur is 2 and oxidation state of the sulfur is 6. So difference of these two oxidation state is equal to 6 minus 2 is equal to 4. So for one sulfur oxidation difference of oxidation state is equal to 4. So for 2 sulfur that will be equal to 2 is equal to 8. So we will get 8 here and 8 here. So these two half reactions are already balanced. Now come over to oxygen. You see here there is one oxygen, but in terms of hydrogen there is 1 and there is 2. So to make it 2 you give 2 here. Now let us calculate the number of oxygen here. 8 to the 32, 3 to the 3 3 is 9 and there is 1. So it is 42. Here 8 to the 16 and 24, and this is 2. It is balanced. This is all about oxidation reduction ion electron method of balancing, basing upon KMnO4 and K2Cr2O7. Hope you have understood the class, and in the next class I am coming with electrode potential and stability of cation in its solution. Thanks a lot for watching the class.